Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're diving deep into Azure DNS Private Resolver, a critical service for hybrid cloud networking. If you've ever struggled with DNS resolution between your on-premises networks and Azure, this service is your solution. Think of it as a translator that enables seamless communication between two different DNS worlds, your on-premises DNS infrastructure and Azure's private DNS zones. In traditional hybrid scenarios, you might have configured custom DNS servers in virtual machines or used complex DNS forwarding configurations. Azure DNS Private Resolver simplifies this by providing a managed, cloud-native solution that acts as a bridge between these environments. It eliminates the need for managing DNS server virtual machines, reduces complexity, and provides enterprise-grade reliability. Throughout this presentation, I'll show you exactly how to implement DNS Private Resolver, from understanding its architecture to executing the specific Azure CLI commands. We'll cover both the inbound and outbound scenarios, so by the end, you'll be able to resolve Azure private resources from on-premises and vice versa. Let's get started. Let me show you the complete architecture of Azure DNS Private Resolver. This diagram illustrates the bi-directional DNS resolution capability that makes this service so powerful. Notice how we have two distinct endpoints: the inbound endpoint at 10.0.1.4 and the outbound endpoint at 10.0.2.4. These aren't just random IP addresses. They're the critical connection points for DNS traffic. The inbound endpoint is where the magic happens for on-premises to Azure resolution. When your on-premises client queries for vm1.contoso.local, that query travels from your on-premises DNS server through your network connectivity, whether that's VPN or express route, to the inbound endpoint. The inbound endpoint then queries the Azure private DNS zone and returns the answer back through the same path. The outbound endpoint works in the opposite direction. When an Azure VM needs to resolve an on-premises resource like onprem.company.com, it sends the query to the outbound endpoint. Based on the forwarding rules we configure, the outbound endpoint knows to forward this query to your on-premises DNS servers. What's really elegant about this design is that it maintains the existing DNS infrastructure on both sides. Your on-premises clients still query their local DNS servers, and your Azure virtual machines use the standard Azure DNS resolution. The DNS Private Resolver sits in the middle, transparently handling the cross-environment resolution. This means minimal changes to your existing setup while gaining powerful hybrid DNS capabilities. Core Components Deep Dive. Now let's examine the core components that make up the DNS Private Resolver service. Understanding these components is crucial because you'll be creating and configuring each one. At the heart is the DNS Private Resolver itself. Think of it as the orchestrator that manages all DNS resolution operations. The inbound endpoint is particularly interesting. It requires a dedicated subnet that must be delegated to Microsoft.network/DNS resolvers. This delegation is important, as it tells Azure that this subnet is exclusively for DNS resolver use. The subnet can be as small as a /28, giving you just 11 usable IP addresses, but that's typically sufficient since the endpoint only needs 1 or 2 IPs. The outbound endpoint also needs its own delegated subnet, separate from the inbound subnet. This separation is by design. It provides network isolation and allows for independent scaling and management. The outbound endpoint is where you'll attach your DNS forwarding ruleset, which contains the logic for routing queries to specific DNS servers. The DNS forwarding ruleset is a container for your forwarding rules. Think of it as a routing table for DNS queries. Each rule in the ruleset specifies a domain name pattern and the target DNS servers for that domain. What's powerful here is that one ruleset can be linked to multiple VNets, allowing you to maintain consistent DNS forwarding across your entire Azure environment. This centralized approach significantly simplifies management compared to configuring DNS forwarding on individual virtual machines. Let me walk you through the detailed sequence of how inbound DNS resolution works. This is what happens when someone on your on-premises network tries to access an Azure resource. Understanding this flow is essential for troubleshooting and ensures you configure the components correctly. The journey starts when an on-premises client, let's say a developer's workstation, tries to access vm1.contoso.local. The client sends this DNS query to your on-premises DNS server, just as it would for any other DNS resolution. Your on-premises DNS server checks its local cache and records. Finding no match, it looks at its conditional forwarders. This is where your configuration comes in. You've set up a conditional forwarder for contoso.local pointing to the inbound endpoint IP address, in our example, 10.0.1.4. The DNS server forwards the query through your secure connection to Azure. This could be over ExpressRoute for low latency, or VPN for cost effectiveness. When the query reaches the inbound endpoint, it's processed by the Azure DNS infrastructure. The endpoint queries the private DNS zone for contoso.local, retrieves the IP address for VM1, and sends the response back. The entire round trip typically takes just milliseconds. Your on-premises client receives the IP address and can now connect directly to the Azure versus M. Notice how the actual data connection goes directly to the VM. DNS is just providing the address resolution. Now let's reverse the direction and see how Azure virtual machines resolve on-premises resources. This outbound flow is equally important because your Azure workloads often need to communicate with on-premises services, like databases, file servers, authentication systems, and more. When an Azure virtual machine queries for server1.corp.local, it uses the DNS servers configured in its virtual network settings. If you've properly configured your VNet, these queries are directed to the DNS private resolver's outbound endpoint. This is automatic. The virtual machines don't need any special configuration. The outbound endpoint receives the query and checks its forwarding rules. You've created a rule that says any query for corp.local should go to 192.168.1.10, your on-premises DNS server. The endpoint forwards the query through your ExpressRoute or VPN connection. Your on-premises DNS server receives this query just like any other. It doesn't know or care that it came from Azure. It resolves server1.corp.local from its local records and sends the response back. The Azure virtual machine receives the IP address and can now connect to your on-premises server. This seamless resolution enables hybrid applications where components span both Azure and on-premises environments. Let me show you how DNS Private Resolver fits into a real-world enterprise network architecture. This diagram represents a typical hub-and-spoke topology that many organizations use. Notice how the DNS Private Resolver is deployed in the hub VNet. This is a best practice that provides centralized DNS services to all spoke VNets. The architecture supports both VPN and express route connections, giving you flexibility in how you connect to Azure. Many organizations start with VPN for proof of concept and migrate to express route for production workloads. The beautiful thing is that DNS Private Resolver works identically with both connection types. Look at the subnet structure carefully. We have dedicated subnets for the inbound endpoint, 10.0.1.0/28, and the outbound endpoint, 10.0.2.0/28. These are separate from your virtual machine subnets, 10.0.3.0/24. This separation is crucial for security and management. The /28 subnet size gives you 16 IP addresses total, with Azure reserving 5, leaving 11 usable, which is more than enough for the DNS endpoints. The spoke VNet, 10.1.1.0/24, is connected via VNet peering. Virtual machines in the spoke can use the DNS private resolver without any special configuration, as they inherit the DNS settings through the VNet linked to the forwarding ruleset. This hub and spoke design scales well. You can add dozens of spokes, and they all benefit from the centralized DNS resolution. It's a pattern I've seen work successfully in organizations ranging from startups to large enterprises. Before we dive into the actual implementation commands, let's ensure you have everything prepared. Proper planning here will save you hours of troubleshooting later. I've seen too many implementations fail because of missed prerequisites, so let's go through them carefully. First, you need a VNet with properly delegated subnets. This is critical. The subnets must be delegated to Microsoft.network/DNS resolvers before you can deploy the endpoints. Each subnet needs to be at least a /28 in size. Don't try to use existing subnets with virtual machines, as the delegation makes them exclusive to the DNS resolver service. You'll need appropriate Azure permissions. At a minimum, you need the network contributor role on the resource group and the VNet. If you're creating new resource groups, you'll need the contributor role at the subscription level. Many organizations have separated network management permissions, so coordinate with your network team if needed. Network connectivity is obviously essential. Your express route or VPN must be functioning correctly. Test basic connectivity between on-premises and Azure before implementing the DNS resolver. Also ensure that UDP and TCP port 53 are open through any firewalls, since DNS uses both protocols. Finally, document your IP addressing plan. Know which IP addresses the endpoints will use, what your on-premises DNS servers are, and which domains need forwarding. This planning phase is where you prevent conflicts and ensure a smooth implementation. Trust me, spending 30 minutes on planning saves hours of troubleshooting. Creating the DNS private resolver. Now we're getting to the hands-on implementation. The first step is creating the DNS private resolver itself. This is the foundational service that will host your endpoints. Let me explain each parameter in this Azure CLI command in detail. The name parameter DNS resolver hub is what you'll reference in all subsequent commands. Choose a name that reflects its purpose and location. I like including hub to indicate it's in the hub VNet. The resource group parameter specifies where the resolver will live. It's often best to have a dedicated resource group for DNS resources to simplify management and access control. The virtual network parameter needs the full resource ID of your VNet. You can construct this ID manually, or use a Z-Network VNet show to get it. The resolver must be in the same region as the VNet. You can't create a resolver in East US for a VNet in West Europe. This is specified with the location parameter. Tags are optional but highly recommended. Use them for cost tracking, environment identification, and automation. In enterprises, tags often drive policy enforcement and backup strategies. Common tags include environment, owner, cost center, and application. When you run this command, Azure creates the resolver service in the background. It typically takes 2 to 3 minutes. The resolver doesn't have any IP addresses yet. Those come with the endpoints we'll create next. Think of this step as creating the framework that will hold your DNS infrastructure. Creating the inbound endpoint. The inbound endpoint is where external DNS queries enter your Azure environment. This is a critical component for hybrid DNS resolution. Let me break down this command and explain what's happening behind the scenes. The DNS resolver name parameter links this endpoint to the resolver we just created. The endpoint can't exist without its parent resolver. The name inbound endpoint hub should follow your naming convention. I recommend including inbound in the name for clarity when you're troubleshooting months later. The IP configurations parameter is where you specify the subnet. This subnet must be delegated to Microsoft.network/DNS resolvers. If you get an error here, double-check the delegation. The endpoint will automatically get an IP address from this subnet, typically the fourth usable IP, as Azure reserves the first 3. You can optionally specify a static IP address by adding private IP address 10.0.1.4 to the IP configurations. This is useful when you want predictable IP addresses for your DNS infrastructure. Just ensure the IP is within the subnet range and not already in use. Once created, this endpoint's IP address is what you'll configure in your on-premises DNS servers as a conditional forwarder. It's the entry point for all DNS queries from on-premises to Azure. The endpoint handles thousands of queries per second and provides built-in high availability. No more managing DNS server virtual machines. The outbound endpoint handles DNS queries going from Azure to external DNS servers. While the inbound endpoint receives queries, the outbound endpoint sends them. This bidirectional capability is what makes DNS Private Resolver so powerful for hybrid scenarios. Notice that the command structure is similar to the inbound endpoint, but we're using a different subnet. This separation is mandatory. You cannot use the same subnet for both endpoints. The subnet parameter points to your second delegated subnet. Like the inbound subnet, this must be at least /28 and delegated to Microsoft.network/DNS resolvers. The outbound endpoint doesn't have a configurable IP address because it's not a destination for DNS queries, it's a source. When it sends queries to your on-premises DNS servers, they'll see the source IP as one from this subnet. This is important for firewall rules. You'll need to allow this subnet in your on-premises firewall. What makes the outbound endpoint special is its ability to work with forwarding rules. It can make intelligent decisions about where to send queries based on the domain name. Unlike traditional DNS forwarding, it can handle multiple forwarding rules with different destinations, making it perfect for complex environments where you have different DNS servers for different domains. The endpoint also provides health monitoring of target DNS servers and automatically fails over if a server becomes unavailable. This built-in resilience is something you'd have to build yourself with traditional DNS forwarding solutions. Now, we create the DNS forwarding rule set. Think of this as the brain of your outbound DNS resolution. The rule set is a container that holds all your forwarding rules and can be associated with multiple VNets. This is where you define your DNS forwarding logic. The name, rule set on-prem forwarding, should describe its purpose. I've seen organizations use names like ruleset prod corp or ruleset dev test to distinguish between environments. The ruleset exists independently of VNets, which gives you great flexibility in applying DNS policies. The outbound endpoint's parameter is crucial, as it links this ruleset to the outbound endpoint we created. Notice we need the full resource ID here. A ruleset can actually be associated with multiple outbound endpoints across different regions for geo-redundancy, though that's an advanced scenario. The location must match your DNS resolver's location. While the ruleset is a regional resource, the forwarding rules within it can target DNS servers anywhere, on-premises, in other Azure regions, or even in other clouds. This flexibility allows you to build complex, multi-cloud DNS architectures. At this point, the ruleset is empty. It doesn't have any forwarding rules yet. Think of it as creating a folder before adding files. The real DNS forwarding logic comes next when we add the actual rules. But having this container structure allows you to organize rules logically and apply them consistently across your environment. This is where we define the actual DNS forwarding logic. Each forwarding rule tells the outbound endpoint that when you see a query for this domain, forward it to these DNS servers. Let me explain the critical parameters and common patterns I've seen in production environments. The domain name parameter must end with a dot. This indicates it's a fully qualified domain name, or FQDN for example. Corp.local with the trailing dot is different from corp.local without it. This syntax follows DNS standards and prevents ambiguity. The domain name can be a top-level domain to catch all subdomains, or a specific subdomain for granular control. The target DNS server's parameter accepts multiple DNS servers for redundancy. In this example, we're specifying two servers, 192.168.1.10 and 192.168.1.11. The outbound endpoint will try them in order, failing over automatically if one doesn't respond. Always specify at least two DNS servers for production workloads. The port is optional and defaults to 53, but you can specify custom ports if your DNS servers listen on non-standard ports. I've seen this in DMZ scenarios where DNS traffic is proxied through security appliances. You can create multiple rules for different domains. For example, you might forward corp.local to your corporate DNS servers, but partner.com to a partner's DNS infrastructure. The rules are processed in order of specificity. More specific rules, like dev.corp.local, take precedence over general rules, like corp.local. This allows you to create sophisticated DNS routing policies. Let's look at some additional forwarding rule patterns that solve common scenarios. These examples demonstrate the flexibility of DNS Private Resolver and how it handles complex enterprise requirements. The first additional rule shows subdomain forwarding. By creating a rule for dev.corp.local, you can route development environment queries to different DNS servers. This is perfect when you have separate DNS infrastructure for development and production. The more specific rule takes precedence, so queries for dev.corp.local go to 192.168.2.10, while other corp.local queries still go to the main DNS servers. The second rule handles reverse DNS lookups. This applies to the 1.168.192.inaddr.arpa domain. Reverse DNS is often forgotten, but it is crucial for many applications. It allows you to resolve IP addresses back to host names. This is used by mail servers for spam filtering, by logging systems for hostname resolution, and by many security tools. The format follows the standard reverse DNS notation, where the IP octets are reversed. You might also create rules for partner domains, cloud services, or even public DNS resolution. For instance, you could forward all queries for Amazonos.com to AWS's DNS servers, ensuring you always get the most current IP addresses for AWS services. Or, you can forward internal SaaS application domains to specific resolvers that know about your custom configurations. Remember that each rule set can contain dozens of rules, allowing you to build sophisticated DNS routing policies that match your organization's complex network topology. Linking rule set to virtual networks. Now comes a critical step that many people miss: linking the forwarding rule set to your virtual networks. Without this link, your virtual machines won't use the forwarding rules you've carefully configured. Let me explain how this works and why it's designed this way. The VNet link creates an association between a forwarding rule set and a virtual network. Any virtual machine in a linked VNet will automatically use the outbound endpoint for DNS queries matching your forwarding rules. This is powerful because virtual machines don't need any special configuration, it just works. In the first command, we're linking the hub VNet where the DNS resolver lives. This enables virtual machines in the hub to use the forwarding rules. The name link hub VNet parameter should be descriptive, as you'll see this in the portal and CLI output when troubleshooting. The second command links a spoke VNet. This is where the hub and spoke topology really shines. Spoke VNets don't need their own DNS resolvers. They use the central one in the hub. You can link dozens or even hundreds of spoke VNets to the same rule set, providing consistent DNS resolution across your entire Azure environment. One important limitation: each VNet can only be linked to one forwarding rule set at a time. If you need different forwarding rules for different VNets, you'll need separate rule sets. This is actually good design, as it forces you to think about your DNS architecture and maintain consistency. Verification and validation commands. After setting up all these components, you need to verify everything is working correctly. These verification commands are essential for initial deployment and ongoing troubleshooting. Let me show you what to check and what the outputs mean. The first command retrieves the inbound endpoint's IP address. This is the IP you'll configure in your on-premises DNS servers. The query uses JMES path to extract just the IP address from the JSON output. If you get an error or empty output, check that the endpoint creation completed successfully. The IP should be from your inbound subnet range. The second command lists all forwarding rules in a table format. This gives you a quick overview of your DNS forwarding configuration. Check that all domains are spelled correctly, with trailing dots, that forwarding is enabled, and that target DNS servers are correct. I often export this to document the DNS configuration. The third command shows all VNet links. This confirms which VNets will use your forwarding rules. If virtual machines in a VNet aren't resolving on-premises domains, the first thing to check is whether that VNet is linked to the rule set. Beyond these CLI commands, I recommend using NSLOOKUP or DIG from both on-premises and Azure virtual machines to test actual DNS resolution. Test both directions, Azure names from on-premises, and on-premises names from Azure. Document the results as your baseline for future troubleshooting. Understanding the dependency chain between these commands is crucial for a successful implementation. You can't create resources in a random order. There's a specific sequence that must be followed. Let me walk you through this dependency flow and explain why it matters. The DNS resolver must be created first because it's the parent resource for both endpoints. Think of it as the foundation of a house. You can't build walls without a foundation. The resolver establishes the link to your virtual network and sets the region for all subsequent resources. The inbound and outbound endpoints can be created in parallel once the resolver exists, as they don't depend on each other. However, they both depend on having properly delegated subnets. If you get delegation errors, pause and fix the subnet delegation before proceeding. The forwarding rule set depends on the outbound endpoint existing because it needs to reference it. You're telling the rule set to use this outbound endpoint to send DNS queries. Without an endpoint, the rule set has no way to forward DNS queries. Forwarding rules obviously depend on their parent rule set. You can create multiple rules in parallel once the rule set exists. Similarly, VNet links depend on the rule set but can be created in parallel for different VNets. This dependency chain also matters for deletion. You must remove resources in reverse order. Remove VNet links before deleting the rule set, remove rules before deleting the rule set, and remove endpoints before deleting the resolver. Now let's configure the on-premises side. This is often where implementations get stuck because it requires changes to your existing DNS infrastructure. I'll show you configuration examples for both Windows and Linux DNS servers. For Windows DNS servers, we use PowerShell to create conditional forwarders. The add DNS server conditional forwarder zone commandlet creates a forwarder for contoso.local pointing to our inbound endpoint at 10.0.1.4. The replication scope forest parameter is important in Active Directory environments. It replicates this forwarder to all DNS servers in the forest, ensuring consistent resolution. For Linux bind servers, you add a forward zone to named .conference. The syntax is straightforward. You specify the zone name and the forwarder IP. Don't forget to reload bind after making changes with RNDC reload or systemctl reload named. A critical point. The conditional forwarder should only include domains that exist in Azure private DNS zones. Don't create a forwarder for your entire domain if only some subdomains are in Azure. Be specific to avoid resolution loops. Testing and troubleshooting is where you validate that all your configuration works correctly. I'll share the systematic approach I use and common issues you might encounter. Proper testing now prevents emergency troubleshooting at 3 a.m. when production systems can't resolve DNS names. Start with basic connectivity tests. From on-premises, Use NSLookup to query an Azure private DNS name directly against the inbound endpoint with the command NSLookup vm1.contoso.local10.0.1.4. This bypasses your on-premises DNS server and tests the inbound endpoint directly. If this fails, check network connectivity and firewall rules. Next, test through your on-premises DNS server with the command NSLookup vm1.contoso.local. This validates that your conditional forwarder is working. Common issues here include typos in the forwarder configuration or the DNS server service needing a restart. From Azure Virtual Machines, test outbound resolution with the command NSLookup server1.corp.local. If this fails, verify the VNet is linked to your forwarding ruleset and that the forwarding rule exists for corp.local. Best practices and production considerations. Let me share some best practices I've learned from multiple DNS private resolver implementations. These tips will help you build a robust, scalable DNS infrastructure that won't wake you up at night. First, always implement high availability. Configure at least 2 target DNS servers in each forwarding rule. For critical environments, consider deploying DNS private resolvers in multiple regions with Traffic Manager for automatic failover. Yes, it costs more, but DNS failures can bring down entire environments. Use network security groups wisely. While you need to allow DNS traffic on UDP and TCP port 53, you should restrict the source IPs. For inbound endpoints, only allow traffic from your on-premises networks. For outbound endpoints, the rules are typically more permissive but should still follow least privilege principles. Implement monitoring and alerting. Enable diagnostic logs for the DNS resolver and send them to Log Analytics. Create alerts for high query volumes, resolution failures, and endpoint health issues. I've seen DNS issues manifest as application problems, so good monitoring helps you quickly identify the root cause. Plan your IP addressing carefully. Reserve IP ranges for DNS infrastructure and document them. Use consistent subnet sizes, like a /28 for DNS endpoints, across all regions. Consider future growth, as you might start with one hub, but later expand to multiple regions. Finally, maintain documentation. Document your DNS architecture, forwarding rules, and IP addresses. We've covered a lot of ground in this presentation, so let me summarize the key points about Azure DNS Private Resolver. This service fundamentally changes how you approach hybrid DNS resolution, eliminating the complexity of managing DNS servers while providing enterprise-grade capabilities. Remember the architecture. Inbound endpoints receive queries from on-premises, outbound endpoints send queries to on-premises, and forwarding rulesets define the routing logic. Each component has a specific role, and understanding these roles is crucial for successful implementation. The implementation sequence matters. Create resources in the correct order. DNS resolver first, then endpoints, followed by rulesets, rules, and finally VNet links. This dependency chain exists for good reasons, as each resource builds upon the previous ones. Testing is not optional. Validate DNS resolution in both directions before declaring victory. Use the verification commands to ensure all components are properly configured. Document your test results as a baseline for future troubleshooting. Looking ahead, DNS Private Resolver opens doors for sophisticated hybrid architectures. You can build multi-region deployments, integrate with multiple on-premises locations, and even extend to multi-cloud scenarios. The skills you've learned today provide the foundation for these advanced configurations. Thank you for your attendance. Please consider subscribing to the channel.